Begin the test by pressing Start on the software screen. Observe the polymer closely for any changes in shape and color. The current rate of extension is 4 mm per minute, which is quite slow comparative to some other polymers. Here, the specimen has fractured in this location, and zooming in, displays horizontal lines in the polymer. These are fracture lines and referred to as crazing lines. Note at the fracture there is a gap between the two halves. At point of fracture, the two grips do not move. That gap is caused by residual elasticity in the material trying to get back to its original shape and size. The smaller the gap between the two halves of a fractured polymer suggests the more brittle the polymer is, and if there is a large gap, it can be deduced the polymer is very ductile. Then retrieve the specimens in reverse order of how it was placed in the machine, by opening the top grip and then the lower grip. The screen shows the plot of force against displacement, and selecting Calculating will display maximum force at the black triangle icon, and the corresponding parallel line along the plot is the line of modulus. Then tap on the Result tab, and the maximum load figure is displayed of 1504.86 newtons. That will be the Fmax used in the tensile strength calculation of force over cross-sectional area. Then tap on Graph, followed by Return for the next specimen to be inserted. Tap onto Before Test and enter the parameters for the next specimen. This specimen is high impact polystyrene. As previously, the specimen has been inserted and tightened in the grips. The relevant data has been inputted into the software, however this time the rate of extension is 36 mm per minute. Starting the test now. Closely note the colour change. It happens quite quickly as it's being pulled in tensile testing. This colour change represents multiple stress crazing within the material. This change is referred to as stress whitening. Stress elongation is observed as the material gets longer. Now there's a fracture. Also note the colour change, or the stresses remained only in the gauge length area. They didn't pass into the shoulders or enter the grip area, which means it was properly gripped into position. There is a large gap between the two halves. At point of fracture, the grips do not move, and the gap represents the elasticity in the polymer. Looking at the plot for the polystyrenes, the first plot in green is the unmodified polystyrene. And the second plot in blue is high impact polystyrene. High impact polystyrene has an additive mixed into it, which is butadiene, and that gives it different properties between the two polystyrenes. The distribution of butadiene into the polystyrene is referred to as a polymer blend. The blending of the polystyrene has resulted in a lower maximum load, and noting the tensile strength is a calculation of force over area, where approximately the areas of the specimens are similar. This plot indicates this polymer will have a lower tensile strength compared to the unmodified polystyrene, which will have a higher tensile strength. Another characteristic visible here is toughness, which is the energy a material absorbs before fracture, represented by the area under a plot. In this case, high impact polystyrene's graph area, when a parallel line against the line of modulus is drawn at the point of fracture, there is a greater area here compared to the green plot, where a similar parallel line against modulus is drawn at its fracture point. The area under that plot is much less. Therefore, it can be deduced without any additional calculation that the high impact polystyrene has greater toughness and the unmodified polystyrene has greater strength. Also note, unlike metals, polymers don't always head towards fracture once the load against elongation begins to fall. In the case of high impact polystyrene, the forces required to maintain the rate of extension dropped, then plateaued for a significant period of time, then the load began to increase once again before it eventually fractured. The high impact polystyrene is also commonly referred to as toughened polystyrene.